Adrenergic neurotransmission. The neurotransmission that takes place in the sympathetic nervous system is called as adrenergic neurotransmission. It is the impulse transmission that is mediated by catecholamines. The catecholamines are norepinephrine, dopamine, and epinephrine. Norepinephrine transmission generally seen in postganglionic sympathetic nerve terminals and central nervous system. Dopamine neurotransmission is also seen in central nervous system, and epinephrine is generally seen in adrenal medulla. Coming to the synthesis, in the first step, phenylalanine will be converted to tyrosine with the help of the enzyme phenylalanine hydroxylase. Here the enzyme hydroxylase is acted, so there will be addition of one OH group to the phenylalanine and it gets converted to tyrosine. In the second step, there is addition of additional OH group for the conversion of tyrosine to dopa. Therefore, it is called as rate limiting step because there is addition of second hydroxylase group, and then dopa is converted to dopamine with the help of the enzyme dopamine decarboxylase. And dopamine is, after the synthesis of dopamine, it is generally taken up to the storage granules and stored there. And all this conversion from tyrosine to dopa to dopamine, it takes place in the axoplasm. Then later dopamine is transported to the nerve terminals and it is stored in the storage granules. Then in the peripheral adrenergic neurons and adrenal medullary chromaffin cells, this dopamine, upon the action of the enzyme dopamine beta hydroxylase, it is called as beta hydroxylase because OH group will be added at the beta position to the dopamine and it will be converted to norepinephrine. Norepinephrine by methyl transpiration, it is converted to epinephrine. Generally, in the adrenal medulla, norepinephrine is released from granules of chromaffin cells and it is N-methylated in the cytoplasm. After the synthesis takes place in the cytoplasm, it is taken into the vesicles by active transport, and this active transport is ATP and magnesium dependent. And this storage happens when the catecholamines are complexed with ATP in the ratio of 4:1. That is, for 1 ATP, 4 catecholamines can be attached. The ratio is 4:1, and after the complexation, it is absorbed on a protein called chromogranin. This absorption on protein will render the amine inactive till it is released. The release happens when the action potential arises on the nerve terminal, arrives at the nerve terminal. After the action potential arrives at the nerve terminal, there will be calcium release by which exocytosis happens and the catecholamines are released. These released catecholamines are transported across the synaptic cleft. After the transportation across the synaptic cleft, it will interact with the adrenergic receptors on the postjunctional membrane. After the catecholamines are released and served its function by acting on the receptors, the termination should take place, and termination takes place mainly by two phenomena. One is uptake and one is metabolism. Uptake generally happens, this uptake is the most important phenomenon for the termination of its actions. The uptake is of two types generally, axonal uptake and extraneuronal uptake. Axonal uptake is called as uptake 1 and extraneuronal uptake is called as uptake 2. In the axonal uptake, it operates at very low physiological concentrations, whereas extraneural uptake operates effectively at high concentrations. This axonal uptake is the most important mechanism for the termination of actions of norepinephrine, whereas in the extraneuronal uptake, generally these catecholamines will be uptaken into the surrounding tissues. Whereas axonal uptake, it will be taken into the presynaptic neuron. In the extraneuronal uptake, it will be absorbed into the surrounding tissues. This axonal uptake requires Na+, K+, and ATP, and this axonal uptake is blocked by cocaine, desipramine, guanethidine, and antihistamines, especially H1 antihistamines, the antihistamines which blocks the H1 receptor. Coming to the extraneuronal uptake, it is less selective and it is not blocked by cocaine, but it is very much sensitive to cortisol and it is of no pharmacological importance. And apart from uptake, there is also termination of action from metabolism. This metabolism happens with the help of the two enzymes. One is monoamine oxidase and the other one is catechol O-methyl transferase. This generally takes place in the cytoplasm. If the norepinephrine is diffused into the circulation, it is destroyed by a COMT enzyme, that is catechol O-methyl transferase enzyme in liver, kidney, brain, etc. And this metabolism does not play important role in terminating the actions of endogenous catecholamines, whereas the most important termination of action is mainly due to the uptake. And the receptors are of two types, alpha and beta, and alpha is again divided into alpha 1 and alpha 2. Beta is divided into beta 1, beta 2 and beta 3. This alpha 1, the actions of alpha 1 are in the vascular smooth muscles, it causes contraction. That is when the adrenaline or sympathomimetics binds with alpha 1 receptors, it causes contraction in vascular smooth muscles and also contraction in genitourinary smooth muscles. In the heart also it increases the contractile force, whereas in the intestinal smooth muscles it causes relaxation. In the liver it causes glycogenolysis. That is generally whenever the glucose reserves are more in the blood, the liver will convert the glucose into glycogen. The glycogen is stored as reserve in the liver. You know, when the sympathomimetic actions increases, the glycogen will be broken down to glucose and glucose is released into the blood. That phenomenon is called glycogenolysis. And also gluconeogenesis, that is synthesis of glucose from non-carbohydrate sources, that also happens in alpha 1 actions. Coming to the alpha 2, it is the actions are generally seen in pancreatic islets, where the insulin secretion is decreased, and in platelets it causes aggregation of platelets, which can precipitate many kind of heart diseases. In the nerve terminals, it decreases the release of norepinephrine. And the alpha 2 actions also includes contractions of vascular smooth muscles. Coming to the beta 1, it increases the force and rate of contraction and also increases AV nodal conduction velocity. In the juxtaglomerular cells, it increases renin secretion, and beta 2 receptor actions include relaxation of smooth muscles and glycogenesis in case of skeletal muscles. Here the glucose will be converted to glycogen and stored in the skeletal muscle, whereas in the liver it causes glycogenolysis and gluconeogenesis, same as that of alpha 1, and in the adipose tissue it causes lipolysis, that is the breakdown of lipids.